Hello everyone. Today I'm excited to present our study. Geometry is often taught through abstract symbols and formulas. For example, Kelsey and colleagues found that students struggle with two-column proofs because they feel disconnected from real-world experiences. Augmented reality can help bridge this gap by giving students hands-on, sensory-motor experiences, making abstract ideas easier to understand. In AR-based education, teachers are key to making new technologies work well in the classroom. Their expertise helps ensure that content is accurate and the tools are easy to use. Teachers also know how to connect AR-based simulations like GeoGebra MR to real classroom activities compared to older tools like GeoGebra Classics. However, AR is very different from the real-world tools and web-based interfaces that teachers are used to. Good design should afford and constrain users in the right way. By focusing on teachers' perspectives, we can build AR platforms that are not only technologically advanced, but also pedagogically effective and intuitive for classroom. Based on these motivations, we aim to understand teachers' perspective on AR-based geometry education. Specifically, we looked at usability issues they faced using a refined definition of affordances and constraints made for AR environments. So we recruited 6 high school geometry teachers. They worked in pairs to solve geometric problems using GeoGebra MR. We recorded their interactions and conducted post-interviews. Then we developed a coding scheme and a decision tree to organize the usability issues we observed based on affordances and constraints. You can see the decision tree on the right side here. Now, I will share what we found. Let's start with sensory affordances. Some problems are technical, but others happen because teachers weren't familiar with AR rules. For example, the limited field of view made it hard to see AR objects. Sometimes, teachers even thought the objects disappeared because they weren't attuned to the logical constraints of AR. Let's see in here.
When I look up, I don't see it. I have to look down to see the triangle.
Second, teachers had trouble figuring out who was controlling the object when multiple people tried to interact with the same one. The system didn't clearly show which user was in control. This pointed to a need for better UX design. Let's see in here.
Get that ray and then pinch it. Do you get the, yeah, there you go.
Wait, was that me? Oh, I don't think it was me.
Now, let's move on to physical affordances. Nearly half of the usability issues we found were related to physical affordances. Many teachers treated AR objects like real ones, but the system only recognized simple gestures like pinching or collapsing, which caused problems. This was both a technical challenge and a sign that teachers were not attuned to the way physical interaction works in AR. Some problems were also related to UX design. For example, teachers struggle with fine manipulation tasks like using menu sliders to turn pictures on and off, or selecting hotspots to resize 3D objects. Let's see here.
So now we can take this point right here and we can put it onto that line.
Nice.
Perfect.
And then if it was exactly on the line, we would see that those measurements would have been the same.
Right, I'm seeing 6.22 and 6.20.
Yeah.
Yes. And that's probably because it's hard to get the exact number.
Next, cognitive affordances. Teachers thought GeoGebra MR had the same features as GeoGebra Classic. They often asked how to use features that didn't exist in GeoGebra MR. Also, some new features in GeoGebra MR caused confusions. For example, there are 2 different symbolic legs that extended from the user's fingers. Let's see in here.
So do I want the large green beam to show up?
No.
Not for
You're
that.
using the white dotted line that turns solid.
Okay.
Another problem was that the system gave confusing feedback. Teachers And even researchers sometimes thought they had to anchor object twice because of this. Finally, let's look at functional affordances. Most UX design suggestions came when teachers compared GeoGebra MR to GeoGebra Classic. They asked for familiar features like algebra tools and labeling options to be added to GeoGebra MR. To sum up, our study introduced a new coding scheme and decision tree to identify usability issues based on affordances and constraints in AR. We found that usability concerns are not only about technology, they also depend on users' expectations and how they perceive constraints. This shows a dual need. First, we need technical and UX improvements, like expanding the field of view, improving gesture recognition, ensuring consistent feedback, and adding familiar features from GeoGebra Classic. Second, we need to help users better attune to constraints. For example, physical affordances issues often came from confusion between real-world interaction and AR logic, while cognitive issues came from expecting GeoGebra MR to work just like GeoGebra Classic. These insights shows that both better design and targeted training are key to making AR effective in education. Finally, I want to thank the Magic Lab team for this great support. And a special thanks to Professor Candace Workington for her key contribution to this study. Thank you.